Hey everyone, this is a video that's on 5.3 and this is the last section that we cover in Math 118. So this is about linear programming, okay? So you might think, what does this mean? So we're not going to be doing any computer programming. So linear programming is a mathematical process that helps with decision making. So we're going to take some of the stuff that we learned in 5.1 and 5.2 and add an additional piece and then kind of decide what is the best. So you can think of stuff that we did in 5.2 as sort of, we have certain restrictions. It could be for supplies. It could be money. It could be like how many workers you have, okay, for running a business. And what are you trying to maximize whenever you run a business? Profit, right? You always want the highest profit or the highest revenue, probably. It's a better idea. And sometimes you want to minimize what? The cost. Okay. So let's look at this first one here and how we can relate it to everything that we've talked about in Chapter 5. So a manufacturer of lightweight mountain tents makes a standard model and an expedition model. So we have two models here. Each standard tent requires 1 hour of labor from the cutting department and 3 hours of labor from the assembly department. And each expedition tent requires 2 hours of labor, so it requires almost double the amount of labor as the standard from the cutting, but not as much as double for the assembly. So it says the max label hours for cutting is 32, and for assembly is 84. If the company makes a profit of $50 for each tent, standard tent, and $80 for each expedition tent, how many tents of each type should we make to maximize the total profit? Right? So this kind of walks us through. So we have a lot of information here, and it says it wants you to, what are the decision variables? Draw a table with the decision variables related to the columns of the tables and summarize the manufacturing requirements, objectives, and restrictions. Okay. So there's a lot that you could say for that. And then it says, write the problem constraints after that table. And then what is your objective function, the problem constraints, and any other constraints. Okay. And then you want to graph stuff. And then, okay, what is the equation of the profit line in slope-intercept form? So you're looking at this. And then it wants you to use that to graph the feasible region and find the optimal solution. And in general, when does it occur, right? So there's a lot to do here. So the book seems to kind of elongate some of the stuff that we do here. So I'll just talk about this particular problem and how it relates to some of these things. So I'm going to write over here. I'll reference some of the stuff that was said, some of those questions that were asked. Some of the questions the notes ask are not that important. Okay, so when you read this, you see that there's really two types of tents we have, right? We have the standard model and the expedition. And, okay, we have certain things that we have to set up here. So I'm going to let X represent for the standard. Okay. Tents, you can think the amount or how many you're going to make. Okay. And then Y is the expedition. Y is the expedition tents amount. So X is just the amount of standard tents and Y is the amount of expedition tents. So you could think, oh, I'm going to produce 100 standard tents. Then that means X would be 100 And then from that, we can use some information here to calculate how many hours the cutting department will use, how many hours the assembly department will use, right? Because we would just multiply by each associated hour for each department, how long it will take. And then we can, if we wanted the profit, if we have 100, then we would do 50 times 100 to get that profit. But you want to think we have restrictions, right? Maybe certain departments only have so many people, so they can only work so long. And we see we have some restrictions here. So this first part here, you can think of these two as your decision variables. Because you can think of it as you're trying to decide how many for each tint you're going to make, right? So I'm not really sure what would work, okay? A lot of values could work, but what I want is values that work and the best value that will maximize my profit, right? Okay. So we have this here, we have our decision. So let's take these two things here and let's create some information from them, some equations, okay? So I'm going to make my table. Right, so you can think we have the standard model, and this is your X. We have the expedition model, where this is Y. Okay. So for the first thing we look at, it says each standard tint requires 1 labor hour of cutting department. So we know we have cutting, right? And then we know the other one is assembly. Okay. So for cutting, the standard model takes 1 hour. So for every one I create, I use 1 hour for cutting, but for the standard model for the assembly, I use 3. And for the expedition model, I use 2, and then I use 4. And then you can think over here is the max that you require. Sometimes it's also the minimum, right? So typically think this one could be or min in certain cases, right? Or you could, okay. So you want to think for cutting, we read through the problem again. It says the max hours, right? So right here for cutting is 32. And the max is, the other one is 84, right? So, I could think of a lot of ways that would work. I could make 10 of the standard, and that would only use 10 hours of cutting because 1 times 10, but then that would use 30 hours of assembly. And then I could make some of the expedition tints, as long as I don't go over the max that I have listed here, these 2 maxes. So instead of trying to think of every possible combination that would work, okay, we're going to write these in terms of inequalities, okay? So you want to think how to figure out like the total cutting, right? So the total cutting would be how many, I'm going to change the color here. How many would this give me? So that would be, so for the cutting, we would have 1x plus 2y. And since this is a max, that would be the highest I can go is 32 or equal to 32. So this would be less than or equal to 32. Okay. Now for the assembly, very similar, but this would be, I have to use the 3 here for the standard model. So that would be 3x plus, and then the expedition is 4 hours per every, so 4y. And then the most is 84. Okay, so I'm going to write that in blue in case it's a little hard to see. This would be 3x plus 4y is less than or equal to 84. So we have, okay, two of our restrictions here, okay, or sometimes people call them constraints. Right, so these are your constraints from the setup of the problem, okay? There's also other constraints, as in it can't make a negative, so these are kind of implied in the problem. So typically x will be greater than 0, and then y will be greater than 0. So just to reiterate, you have 1, 2, 3, 4 constraints here, okay? So I'm just going to extend this a little bit because the two at the bottom are kind of implied. Some books will call these implicit because it's implied, okay? So we have these constraints, okay? So on Desmos, we could graph all of these, like from 5.2, and get a feasible region, right? All the points in that region that satisfy all of these at once could work, right? But I want to know which value is the best, okay? So how would I get the best value? Well, the one that gives me the highest profit. Well, what's my profit? So you have your decision variables, you have your constraints from your problem, and then you want to think, how do I know, how could I get my answer? Here I'm looking for the profit, here max profit. So in these problems you have something called an objective function. Typically this is what you're trying to maximize or minimize. Okay. So in this case your objective function would be your profit. So your profit equals, so you can write this under your table if you want, when you're thinking of your profit. How much do you get per standard model? It says you get 50. And how much do you get per expedition model? You get 80. So we could say it's 50x, because I get $50 for every standard I sell, plus 80y. So this is what I'm trying to get the highest one, right? So setting up the problem should be very similar to like 5.1, 5.2, getting those inequalities. Remember those key words, what the inequalities mean, like less than, greater than, at most. This is the max, this is the min, okay? And also these right here, I call these implicit constraints. Sometimes the book will call them non-negative constraints as well, okay? So just to reiterate, we want the max for this, okay? So you could do a few things here. Okay, so I will walk you through the problem. So we talked about the constraints, we talked about the objective function decision stuff. So now we're at this point here, graphing the feasible region. So you want to graph both of these. So since I have non-negative constraints, I'm just going to assume I'm in the first quadrant. Okay. All right, so for the cutting, remember we have, you have these inequalities, which just assume I'm in the first quadrant, so I've already kind of got that there. I'm only going to look at that. First quadrant from what we have here. So remember the cutting constraint was x plus 2y is less than or equal to 32. Right? So how would I plot this? So I'm going to let's see, the simplest way. So let's see, let's see how many I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to count by 3. Or maybe a little bit more. Let's do 3. So this is 3, 6. Well, maybe a little bit higher. I'll make it a little easier on us. I'll count by 5. So 5, 10, 15, 20, 25. And I will kind of erase this because the numbers will get cluttered. So I'll say this is 10, 20, 30, 40, 50. And then likewise, 10, 20, 30, 40. So to plot this first one, I know that if you practice from before, just to kind of reiterate, you could draw this on Desmos, so just practice with that. But just remember, if I want to draw this on here, you could get the intercepts. Okay, that's one way. Now, if you can't get the intercepts, like if your MyLab doesn't let you graph the intercepts to graph your line, always pick 2 points that you can see. It might be like a value at 5 and a value at 10, or a value at 20 and 30 if you can't get your intercepts. Okay. So for this first one here, the x-intercept is going to be 32, 0. And then the y-intercept will be 0, 16. Right, so I'm going to graph these two. So 0, 16 is here. And then 32, 0 is here. And then I'm going to draw these like this. And then since it's less than, if I check the origin, I see that it's true. So you want to think if I do 0 plus 2 times 0 is less than or equal to 32. Is this true? Yes, because 0 is less than or equal to 32. So I'm going to shade. So I'm going to shade below, right? So I'd be shading like this. So I'm going to shade in a different color, just so we're on the same page. Right, so I have that it's below. Okay. And then I need to graph the one for the assembly. Right, so for this one, it is 3x plus 4y less than or equal to 84. So if you do the same approach, get your intercepts. So look at the previous, what would it be? Or remember, you could look at Desmos, get them that way. So your x-intercept here will be okay, 28, 0. And your y-intercept will be 0, 21. Okay, so I'll do the y first. It's right here. And then the x is 28, so it's right here. So we see what happens. I'm going to cross. Okay, it looks like it's going to cross around here somewhere. So we'll see on Desmos what a more accurate this would be. But it should be around this. So as I said, when you draw by hand, you might be a little off like I am. Okay. So where would I shade? You can probably guess if it has, you see this has a very similar setup. You have x plus y. They're both positive, less than a value. So that's always usually shading below. So then if I shade this one below, I'm going to color the feasible region now in black. So it's going to be all of this. Okay. And we'll see that a little bit better in Desmos. So your corner points in this feasible region would be here. Okay, would be here, would be here, and would be here. Okay. So your corner points are 0, 0. 0, 16. And then 28, 0. And then that 26 now. As I said, getting that intercept by hand, you could solve each one of these, set them equal, do those any other one of those methods we talked about before. But as I said earlier, Desmos is the best key. So let's graph both of these on Desmos just to double check real quick. So our first one was x plus 2y is less than or equal to 32. So we see it's right here. So I'm going to zoom out just a bit so we can see it. Right. Now, for this other one here, I'm going to graph it 3x plus 4y is less than or equal to 84. Right? So we see where do they overlap. Okay. And I'm going to do my other points just so you can kind of see. Right. So one thing to note is when you graph so many, it might be hard to tell where is the feasible region. So one thing you could do is you could technically edit and change the color. So you could hit the cog here, right? So it's at the very top on the right, under where you enter all the stuff in. There's a cog right beside the double arrows pointing to the left. You click on that, and then I can change it. And let's say I want to use orange. And everything, I would just click on the color, and I can change it to orange. Right? And even I can change it, the fill, I could change that value if I want it to be not as dark. Like let's say if I put this as 1, what happens? It's super dark. I can't really tell any fill, right? So I could do a little bit lighter, like 0.2, right? And then you could change the other ones as well if you wanted to change them all to 0.2. If you're having trouble seeing, where is the shaded area at? Right? So now if we look at this, we kind of see like the darkest shaded area would be, right here. Right? So these are your 4 corner points, okay? So I do know that the same color sometimes helps you see the darker one, because all the different colors can be very hard to see certain color combinations. So we see we have this. So why are we looking at the corner points? Well, there is a lot of math behind this, right? But the shortcut is one of the corner points will actually help you get the value that maximizes or minimizes your objective function. And you want to think, why is that? You can kind of see it as because the corner points kind of lie on the boundary line, and that's why. That's some intuitive thinking behind there. One way the book approaches this is, okay, what it wants to do is if I took my slope, right? So if you take, so we're not done yet. So we'll finish the problem and we'll talk a little bit more about the theory. So check which corner point will maximize the objective. So remember, in some cases you might have to minimize the objective function, okay? Typically cost, you want to minimize. Profit, you want to maximize, okay? So you want to think, you're going to check each one, and over here, I'm just going to make like a tiny table right here. I'm going to put profit. So remember that equation was 50x plus 80y. So you would just check each one, right? So for like 0, 0, so I'm going to kind of erase this here. So you want to check each one. Hold on, let me see if I can do this a different way. I'll do this. No. Where'd it go? Okay. Magic, right? So check each one. So what that means is I want to plug it in. So this would be 50 times 0 plus 80 times 0. And this is 0. So obviously if you don't make no tenths, you're not going to make any money. And then you check the next one, 50 times 0 plus 80 times 16. All right. What would that give me? Okay. And then 50 times 28 plus 80 times 0. And then last one, 50 times 20 plus 80 times 6. Let's get our calculator out. Let's see what we would get here. Okay, so let me get my calculator. And let's calculate these. So we get the first one. If you just make 16 of the expedition, you get 1280. If you make 28 of the standard, and then you make none of the expedition, you get 1400. Right? And then last one, you get 1480. It looks like this is the max here. So I would make 20 of the standard model and 6 of the expedition model. Okay. That would be the optimal solution. So how the book will, you could read through it, how it breaks in the corner points, right? And I usually say in this sort of model, the corner points are nice because you just check them all. Because if you're dealing with a min, it might be one of the points on the intercept, okay? Like it might be one of the points on the, not intercept, yeah, where you can think of intercept, okay? As in on the x-axis or y-axis. And typically when you have a minimum, you're not going to have the origin as one of your corner points if you're looking to minimize some like the cost, okay? So one thing to note is that the book does emphasize, like right here, it wants you to write the equation in slope-intercept form. So hypothetically, if you wrote your profit, right, as slope-intercept form, you solve for y, you'll get in the end y equals let's see, 50x minus p over negative 80, right? If you move over the minus 80y, divide by the minus 80. And if you simplify, you get y equals negative 5/8 x plus p over 80. Making you rethink, what does this even mean? Okay. So what happens here is you can take this and I can draw this on my graph up here because I know what the slope is, right? And the intercept would be p. Okay. And you might think, well, how would I get my p, right? Well, so if you think about it, your p is unknown, right? And if your p is larger, what's going to happen? Then this line, right? You can kind of think if I draw on this picture up here, I would have something like, let's say, it would look, I could draw something like this. Now it's a negative slope, so it might look something like this, right? And then this would fluctuate. So this line would move up and down based on what my p is. right? Because if it's larger, it's going to be further up because why? The y-intercept would be larger. Okay, so the book does talk about it this way, and if you move this line up and down, this imaginary line that I have right here, when does it actually go into my feasible region? The first point that it would hit it would actually be at the 26. Okay, which happens to be when we maximize profit, right? Because that's when this line will first hit it, and if it's the first time it's going to hit this feasible region, that means the intercept is the largest, so it would mean it has the largest profit. Okay, but I will say that trying to think of it this way can be confusing, right? And pretty much what it boils down to, and how I was explained to this, like when I learned linear programming, was just look at your corner points. Get your corner points in your region, go through each one, plug them into your objective function, which one works, okay? So the book does explain it by using writing a line and doing it that way. So let's just look at the next problem and see what happens, okay? Yeah, and it says, in general, the max will occur at one of those corner points. Okay. So we have the Matron 1. You can practice this one on your own. So pretty much reiterating, okay, what are your x and y? Okay, so x is what? Y is what? Okay, what do they represent? Summarize the material in table form. Okay, so that means you make your table. Determine the objective and write the linear functions. Right, so what's your objective function? So it's like you're going to maximize or minimize what? Like in the previous problem, we wanted the max profit. Okay. What are your constraints? So the constraints from the problem, and then the non-negative constraints. And I mean, that's kind of, I usually just write the constraints all together. Okay. So a linear programming problem wants you to find the optimal value, the max or min, of some of some objective function. So typically it's in this format. And the previous one was P instead of Z because P stands for profit. We have our decision variables X and Y, and we have some constraints we're going to make. Just think we always have these non-negative ones here for word problems. Get your feasible region, and it says look for your optimal solution. And as I said, most of the time it will be one of your corner points. So there's a lot of theory here. So if the optimal value of the objective function in a linear program problem exists, then it must occur at the corner point. So that very confusing, like making a line, moving it up and down, as I said, very confusing. Okay. We can just think, oh, I don't need to do that. I just know it's a corner point. Okay. I'm not trying to make anyone's brain explode. Okay. So find those corner points. That's what we practice in 5.2. So remember, we practiced this in 5.2. Okay. So then the next theorem talks about if it's bounded, then the min and the max will always exist. Okay. That means if I shade something in, if I have a graph, this, for instance, and let's say this is bounded, this is my feasible region, then I know I have a max and a min. Okay. If it's unbounded, then I have a min, but I don't have a max. So what unbounded means, if you want to draw your lines, and let's say it's unbounded, so it's all of this out here. It's going to I would keep shading forever in that direction. Then I know I have a minimum, but I don't have a max, because if you tell me a point that would give you a large value, I can tell you an even larger point. Okay. And then last one, if it's empty, so that means there's no feasible region, then there's no max or min. Okay. This kind of walks you through making a corner point table, finding optimal solutions, and then interpret that. Kind of what we did in the practice problem at the beginning. Okay. So minimize or maximize z. So what is the minimum? So min z. So the minimum value of z, and then the maximum value of z. Okay. So what would those be? So as I said earlier, you could draw a picture here, but you have what I would suggest, since the rest of these are just practicing, okay, practicing, is just practicing on Desmos. Okay, so I'm going to go through A. Let me take a picture of it. And we will key this in Desmos. So the one thing that typically will trip up people is you try to graph your objective function. So remember, we're only going to graph these. We're not going to graph this. This is separate. This is your objective function. So this is your, if I can actually write today. Right, objective function. So let's go to Desmos. Let's key this in. So we have, remember, I'm not keying my objective function, so I'm going to key in my 2x plus y. That's less than or equal to 20. And then I have 10x plus y is greater than or equal to 36. And then I have 2x, oops, plus 5, y is greater than or equal to 36. And then I have my two constraints, okay? Which was greater than 0. And you might think, where is the shaded area? So as I said earlier, remember, you want to probably change it to all the same color. So I'm going to stick with orange. Right? And if you just look at this, where does it look to be the darkest? So it might be hard to tell. So I'm going to change the coloring a little bit. Okay, so let's change the fill to be a little bit smaller. All right, so I'm just clicking on it, making the smaller value. All right. And hopefully you can see. So one thing to note, I'm going to take off the two at the bottom here. If you look at this, you can easily tell what all three of those cross. It's that triangle. And the two non-negative ones would just tell you it has to be in the first quadrant. So pretty much since this triangle is in the first quadrant, that's going to be what it is. So I can see these now that my shaded area will be here, here, here. So these within this triangle here, okay? So those values. So let's take a picture. I can record those numbers. Right. So your corner points that we got were 2, 6, 10, 3, 6, and then 8, 4. So then what's your z value here, right? So that would be using your objective function, okay? So this would be, so remember your z is 3x plus y. So this would be 3 times 2 plus 16. That will be 22. This next one will be 3 times 3 plus 6, and that is 15. And this last one will be 3 times 8 plus 4, and this is 28. So it looks like here, the max and minimum, maximize and min, so the max value of z is your 28, so that occurs when x equals 8 and y equals 4. And the min would be here. Right, so this is your max, this is your min. It's 15 when x is 3 and y is 6. Okay. So for the next one that we have, very similar. We want to minimize and maximize z. So what would be our, so just think this is your objective function here. So we're not going to graph that. We're going to graph the other ones. All right, so let me take a picture. And one thing that you'll notice is this one has a peculiar one of this one right here. Okay. So let's go over to Desmos. Let's plot these in. Right. So I'm just going to retype in the first one here. This is 6x plus 2y. And we are greater than or equal to 36. And the next one is 2x plus 4y and greater than 32. And then the third one, y is less than or equal to 20. All right. So when you look at this one, it looks kind of weird, but you see that chunk. So starting here, going down to there, to here, to here, and then all of this, if I go to the right, from that top point to the right. So it's like a rectangle with some pieces broken off like a candy bar if you bit into it. Right? So all of this would be your feasible region. So since this is, remember this is an unbounded one, okay? We can only do what? Find the minimum, okay? Because any point to the right would be keep getting larger and larger and larger, so you wouldn't have a max here that you could find, okay? So if we go back, we're going to think minimum, minimize only, because unbounded. So let me go back. I forgot to take a picture of my graph. Okay, so let me do that real quick. Let me relabel my corner points. Just clicking on them, no, not that one. Okay, if I could not click the, 1 second. I know I have that one. Okay. And since I know it's unbounded, I only have a minimum. All right, so your corner points were 0, 20, 0, 18, 4, 6, and then 16, 0. And then your z, which we said was 10x plus 20y. What would your z be here? So for the first one, it'd be 10 times 0 plus 20 times 20. So that would be 400 altogether. Okay. The next one is 10 times 0 plus 20 times 18. This would be 360. Okay. The next one would be 10 times 4 plus 20 times 6. So that would be 200. Oh, not 200. 160. And then the last one, 10 times 16 plus 20 times 0 would equal also 160. So we see that the minimum occurs at 2 places, which is perfectly fine. So a minimum is minimized at 4, 6 and 16, 0 with the value being 160, okay? So the next problem that talks about, there's another MASH problem here, and then it talks about medications, okay? So just think, as you do your problem, if there's a problem where they don't intersect at all, then there is no max or min, okay? So you can look at the book. So up here, remember there is, if it's bounded, and then not bounded, and then known. So I would suggest looking at, there's no question in the book, like practice problem, but if you look at, so example, not example, it's on page 278. It's right before example 3. Okay. So the last thing we talk about here will be, there's this example on some medication, going through the whole process. There's a match problem. And then that concludes everything, okay? So let's talk about this medication problem. So a hospital patient is required to have at least 84 units of drug A and 120 units of drug B each day. So I already have 2 different drugs here, A and B. Each gram of substance M contains 10 units of drug A and 8 units of drug B. Each gram of substance N contains 2 of A and 2 of B. So initially when you read this, you might have thought A would be X, B would be Y, but by reading the problem more, we see that M and N would be X and Y, because it says that suppose that both M and N contain some undesirable drug D, 3 units in M and 1 unit in N. And it says how many grams should be given of M and M to be mixed together so I can meet those minimum requirements, but minimize drug D. Okay. So when you see this, okay, it says how many grams of each substance. So this kind of reiterates that X would be the amount of M in grams, and Y is the amount of N in grams. So if you make our table from before, remember we have drug A amount, drug B amount, okay? And then we have a substance M and N. So we make our table. So we have M, N, and then the minimum that we need. So for drug A, it says that how much does, so it says here, M contains 10 for A and 8 for B. So I'm going to say this is B here. The second row is B. So, and 8 for B. And then drug substance N contains 2 for A and then 4 for B. And then I need how many of A? What's the minimum? 120 from the first. Sorry, that's for B. 120 is for B, and 84 is for A. Okay. Remember, M is X, N is Y. So then from these two, I can set up my two constraints. Remember, automatically, I have my non-negative constraints. Okay. And then my first equation would be 10x, this is for A, plus 2y is less than, not less than, I need minimum, so that's going to be greater than or equal to 84. And then for drug B, 8x plus 4y is greater than or equal to 120. And then think your drug D is you want to watch out for, you want to minimize this, but how many of drug D is in M? That's 3. And then 1 is in N. So your objective function is D equals 3x plus 1y. And you want to minimize this, okay? So we have our constraints here. So what we would do is we look at Desmos, get our feasible region, get our corner points, and then see which ones it would be, okay? So let's graph Desmos and get our corner points, okay? So our first equation was 10x plus 2y is greater than or equal to 84. So I'm going to zoom out just a bit so I can see everything a little bit clearer. And then the next one was 8x plus 4y is greater than or equal to 120. So I can kind of see that the darker region is on the top right. So this is unbounded. So I know that those 3 would be my corner points because that feasible region is the dark top right. So let me take a picture. So from this, we got our corner points. So our corner points here. And then you want to think the d value. Remember, d value is 3x plus 1y. So the corner points was 0, 42, 4, 22, and then 15, 0. So let's plug it in to see which one gives us the smallest amount of substance, D. So 3, 0 plus 40. Whoops, let me write that nicely better. 1 times 42. So this would just be 42. All right. So then the next corner point. So this will be 34. And then the last corner point, 3 times 15 plus 1 times 0, which gives me 45. So if I want the minimum, it looks like 34 would be the smallest over here. So this would be the amount of M and N I should take. So 4 grams of M and 22 grams of N give 34 grams of D, okay? Which is the minimum here. So I hope you liked this video. As I said, this is the last video for this semester. So please let me know if you have any questions. And as you're preparing for the final project, which will open soon, I am opening up all of the previous projects, and you can practice those as much as you like if you want to prepare for the final, or you want to increase your grade maybe on one of those main 4 projects. Thanks again.